In this lecture, we shall learn about escape speed for a particle from the surface of any celestial body in general and from the Earth's surface in particular. It's common knowledge that if you stand on the surface of the Earth, that is the ground, and throw a small particle, say a pebble or maybe a coin in your hand or a ball, vertically upwards with a small speed, the particle reaches a given distance, a height above the ground, and then returns along the same path. That is, goes up and then comes down. And you are aware that the maximum height reached by the particle before it stops momentarily and starts the return journey, this h max is a function of the initial speed of throw. Greater the value of this u, greater the value of this h max. So therefore, suppose you throw the ball with a greater speed now, a little larger arrow than before, and then again the particle reaches a greater height before returning back to the ground. It is going up and coming down along the same line. So you get enthused. You just apply even a greater force and a greater initial speed, as I am showing by this increasing length of this arrow, and accordingly the particle also reaches a greater height above the ground before then again returning back to the Earth's surface. So while the value of h max goes up, you have got a legitimate question that is it possible to throw the particle with a great enough speed so that it never returns to the Earth's surface, it escapes beyond the Earth's gravitational field? The answer of this question is yes, provided you throw the particle with a minimum speed equal to the escape speed at the surface of the Earth. So the escape speed, that word has, the phrase has already have come into discussion, and therefore let me introduce the statement which gives you the definition of escape speed. The minimum speed with which a particle must be projected so that it may escape the gravitational attraction of the Earth is called the escape speed for the Earth. The definition can be of course improved. I have already said we are discussing the Earth in particular. Escape speed is a phrase, a term that is valid for any celestial body, and it also depends on exactly from which position, the surface or a mountain top or a crater bottom, where from you are just throwing this particle. We'll come to that step by step. Let us go on to a new page and start deriving an expression for escape speed with some simple physical assumptions. Now, to get an expression for escape speed for any planet, I want to keep my discussion general, so I'm considering a planet here which may be extended for the Sun, other planets including the Earth, any moon of the planet, and so on. Therefore, I consider this spherical planet. Let the mass of the planet be mp and the radius of the planet is taken to be rp. This is the center of the planet C, and you know that for a spherically symmetric celestial body, the whole mass can be thought to be concentrated at the center C for any external point. So here is a particle that is being launched vertically from the surface of this planet. You know the meaning of vertical launch is that if I could have drawn a line, radial line joining the center to the particle's position, the particle is being thrown in the radially outward direction, a direction that cuts the tangent drawn at this particle's position normally. That is the meaning of vertical launch, and I assume that initial velocity of launch is u. The mass of the particle is taken to be m, and once the particle is thrown, it travels a distance further from the center of this planet radially, and this is the farthest point where the speed of the particle becomes zero momentarily. So I also want to take two more quantities in my figure, that is at the farthest point from the planet, the maximum distance of the particle from the center of the planet is r max, and correspondingly the height reached by this particle above the surface of the planet is taken to be h max. We shall require these two quantities during the derivation, and we make the physical assumption that the planet is non-rotating to keep the calculation simple, and also importantly there is no significant atmospheric resistance on the particle's motion. That is, we ignore any work done by any external dissipative force on the planet plus particle system. Once we make the assumption, we know that for the planet plus particle system, the only forces doing work on this system will be the internal conservative force of gravitation, and therefore we can apply the principle of mechanical energy conservation for the planet plus particle system at the initial situation where the particle is being launched from surface, and the final situation when the particle has gone the farthest from the planet. So here are the initial, this is the initial situation, particle at the planet's surface, and this is the final situation when the particle is farthest from the planet. So let me write it here. At the surface, that is when the particle is at the surface of the planet initially at the time of launch, what is the mechanical energy for the system? The kinetic energy of the system is comprised only of the kinetic energy of the particle. This earth has got no motion in this regard in this discussion, and therefore we consider that K1 is given by half into mass of the particle into the initial speed u square. What about the gravitational potential energy for the particle plus planet system? Well, you have already known the formula that for any spherical body, you know the formula of gravitational potential. Therefore, you will agree E1 is given by minus gravitational constant G into mass of the planet MP into mass of the particle M divided by the distance between the particle and the planet's center, that is equal to the planet's radius. This is coming out to be simply Rp. So here are the values of K1 and E1, and they together form the total mechanical energy of the system initially at the time of launch. Finally, when the particle goes farthest, at the farthest point from the planet, what is the value of K2, kinetic energy? Well, the Earth's motion is not considered and the particle has momentarily, let me write it here as well, when the particle reaches the farthest from the planet, momentarily its velocity becomes 0. Therefore, we understand the value of K2 becomes half into m into 0 square, speed becomes 0, and K2 is 0 for this particle plus planet system. What about the gravitational potential energy for the system when the particle is here? At this point, the distance between the particle and the center of the planet is taken to be R max. So I shall take this value of R max only here and write down potential energy is minus G into mass of the planet MP into mass of particle small m divided by the distance R max between the center of the planet C and the particle's position. This is R max here. So as we said that we ignore any dissipative force or the work done by it on this planet plus particle system, and only force doing work on the system is a conservative force of gravitation. The initial mechanical energy of the system must be equal to the final mechanical energy. Therefore, by applying the conservation principle of mechanical energy, we could write down, well, I have taken some liberty with my writing to acquire some space, and I was telling you that applying the mechanical energy conservation principle for this planet plus particle system, that initial value of K1 plus U1 must be equal to the final value of K2 plus U2. And putting the values written above, I am getting it, half into m into u square minus g into mp into m divided by rp must be equal to 0 minus g into mp into m divided by r max, where r max, as you can see from the figure, it is the maximum distance attained by the particle from the center of the planet. So, looking at these four terms, we see that the mass of the particle cancels out from each of them. So, it is not significant any further that the mass m of any particle that was launched here. And from here, little bit of rearrangement will be giving us that half u square is coming out to be gmp divided by rp minus gmp divided by r max. If I could take gmp as common, I would get inside bracket 1 upon rp minus 1 upon r max, is not it? And it follows therefore that the initial speed being u square is coming out to be twice gmp into inside bracket 1 upon rp minus 1 upon r max. That is my first important result. I'll be calling it equation number 1 for future reference, and let us look into it and look at the different terms involved. We are getting here u square is equal to twice g into mp in bracket 1 upon rp minus 1 upon r max. Here u is the initial speed of launch of the particle from planet surface, capital G gravitational constant, mp is the mass of the planet from which the particle is thrown, rp is the radius of the planet, and r max is the maximum distance attained by the particle from the center of the planet. So we have already hit upon the equation that is numbered 1, which will be giving us eventually the value of escape speed from the planet's surface, but I want to deal with it a little more to get an expression for the maximum height reached by the particle as a function of u. And remember, this will be not as easy as we have done in kinematics much before, because we know now that if the height is considerably large, the value of free fall acceleration on the planet's surface and above, as you go away from the planet's center, it keeps changing as a function of h. Therefore, we shall take note of that and see how to get this h max as a function of this u. And for doing this, let me write my next step. From equation number 1, I could write down that u square is equal to twice g into mp. Let me divide outside by rp square, and inside the bracket I get then, well, rp square by rp is coming out to be simply rp minus, I have to multiply by rp square in numerator, next term, divided by, now what is this r max? Looking at the figure, the r max is nothing but the radius of the planet, that is rp plus h max. So, let me write in the figure as well, this is the radius of planet plus the height above the planet's surface. And I put the same thing here as well, is rp square by rp plus h max. We are trying to find out this h max as a function of u. Once we reach here, you see that as we have learnt earlier in my class on gravity, I am writing it somewhere here, that on the surface of the earth, the acceleration due to gravity could be expressed to be capital G, gravitational constant, into mass of the earth divided by the square of the radius of the Earth. This was I had done regarding the Earth's gravitational field or acceleration due to gravity. But extending this one for the planet also, I could write down that the acceleration, that is free fall acceleration on the planet's surface Gp, I repeat, this is the value on the surface of the planet, is given by gravitational constant into mass of planet mp divided by radius of planet rp square. Therefore, looking into it, I can see here that this quantity g into mp by rp square is nothing but the free fall acceleration on the planet's surface. So I could write down this is coming out to be twice gp, and inside the bracket I am getting, of course, rp minus rp square divided by rp plus h max. We have to do some manipulation, and I'm afraid I have no space left on this page. I'll move on to the next page with the result and see how we can express h max as a function of u. But before that, look at the steps once again and take care of the substitution. In the last step, this gp is standing for the free fall acceleration on the surface of the planet. Let us move from here and pick up the same thing into the next page. So we are onto a new page and we have come so far. So picking up from here, let me write down u square is equal to twice gp into, entering inside the brackets, in denominator we have got rp plus h max, and in numerator it is rp square plus rp into h max minus rp square, isn't it? So the rp square get cancelled in the numerator and we are having u square equal to twice gp into rp into h max in numerator divided by rp plus h max. So we are getting u square is equal to twice gp rp into h max upon rp plus h max. So multiplying diagonally, we could write down in the next step that rp into u square plus h max into u square equal to twice gp into rp into h max. To make h max the subject, in the next step I keep on the left hand side rp into u square and collecting the terms containing h max on the right hand side and taking h max common, we have inside bracket twice gp into rp minus u square. Therefore, finally, we are getting h max equal to rp into u square divided by twice gp into rp minus u square. That is my next important result, and I shall call it equation number 2. So let's see what we have got. We have got that the maximum height reached by the particle above the planet's surface, that is h max, equal to planet radius rp into speed of launch squared u square divided by twice free fall acceleration on planet's surface, that is gp into rp minus u square. Remember, in this calculation we have taken into account the fact that the free fall acceleration on the planet keeps on changing as the particle reaches significant height above the planet's surface, unlike the simplified case in the kinematics chapter. So we have got two results so far. Equation number 1 giving me the speed of launch in terms of given quantities, and equation number 2 giving the maximum height reached by the particle above the planet's surface in terms of the speed of launch. So we shall now return to equation number 1 and use the definition of escape speed in equation number 1 to get an expression for escape speed. So let us move on to the next page with these two results, equations 1 and 2, and see how to get the expression for escape speed next. So we are on the new page with our old figure and the two equations obtained so far. I was telling you we can return to equation number 1 now and recall the definition of escape speed to find out the value of that in terms of the given quantities. So let me introduce the definition once again. We told you earlier that the minimum speed with which a particle must be projected so that it may escape the gravitational attraction of the planet, in my case it's a planet, is called the escape speed for the planet. So I shall keep this statement by one side tucked at one corner for any reference and make use of this to get the value of escape speed. Now what exactly is the meaning of escaping the gravitational attraction of a planet? You recall the formula for a spherical body. The gravitational field due to a sphere of mass m at an external point at distance r from it is given by minus gravitational constant g into mass of the spherical body divided by square of the distance of the external point from the center of the sphere, that is r square, into r cap. Well, of course, minus r cap means that direction of field is toward the center of that sphere. So you can see it from here, the magnitude of E is simply gm by r square. And when you escape the gravitational attraction of a spherical planet, it means the value of E becomes 0. But the equation shows here that E can become 0 only when the denominator, that is r, becomes infinity, is not it? Only at infinite distance from the center of a planet, the gravitational attraction of the planet on the particle ceases. It stops. There is no further field or attraction. Therefore, I have to consider equation number 1. And to get escape speed, what we'll do is that we shall substitute u by a new symbol, that is VESC. This ESC is a subscript standing for escape speed that is required, the minimum speed required to throw the particle so that it doesn't return to the planet's surface once again. And in the expression, this R max will be actually equal to infinity, a distance, a value larger than any value you can think of. So when you make these two substitutions in equation number 1, we are getting that V escape square is equal to twice G into MP inside the bracket 1 upon radius of the planet RP minus 1 upon infinity. The value of R max must be infinity so that the particle escapes gravitational attraction of the planet and doesn't return to the surface anymore. And since 1 upon infinity is 0, my equation is boiling down to V escape square is equal to twice GMP divided by RP, is not it? 1 upon infinity is 0. And from here I am getting that the escape speed from the surface of the planet is given by square root of twice gravitational constant capital G, mass of the planet MP divided by RP, radius of the planet. Here is the expression I was looking for. We have got escape speed of any particle, because the mass of the particle doesn't come into the expression, from the surface of the planet is given by square root of 2g mp by rp, symbols having their usual meaning. I might improve it even further, and since we have seen earlier that on the surface of planet the free fall acceleration Gp is given by G into mp by rp square. Therefore, I could write down this quantity gmp by rp. You can check yourself. This is coming out to be the free fall acceleration on planet surface multiplied by the radius of the planet rp. Just check it from here to this. And once we are here, we can substitute gmp by rp inside the square root and could write further that the escape speed from the surface of planet could also be expressed to be square root of twice free fall acceleration at planet surface small gp into radius of the planet rp. Let me call it equations 3a and 3b because there are variations on the same expression here, and these are the equations which give the escape speed from the surface of any planet. I can extend it easily for any other celestial body like the sun, the moons of a planet, or our own Earth. So, if I could write it for the Earth itself, I would write down escape speed from the surface of the Earth is given by square root of twice capital G into mass of the Earth me divided by the radius of the Earth re, the whole thing under square root, or alternatively this is coming out to be square root of twice the acceleration due to gravity on the Earth's surface, symbol is G only, into the radius of the Earth re. I am calling it equation number 4 for distinction. You have got quite a few equations here and you can have a look at them before I get the value of escape speed from the surface of the Earth. So to get the escape speed from the surface of the Earth, we need the value of mass and radius of the Earth. Let us take down this data. Already we know that capital G, gravitational constant 6.67, 10 to the power minus 11 Newton meter square per kg square. The mass of the Earth me, which you might remember, 5.98 into 10 to the power 24 kg. And the radius of the Earth, RE, is equal to 6.37 into 10 to the power 6 meter. Putting these values in equation number 4 above, we are getting escape speed from the Earth's surface is equal to square root of 2 into the value of G, that is 6.67 into 10 to the power minus 11 Newton meter square per kg square, into me, the mass of the Earth, 5.98 into 10 to the power 24 kg. Whole thing under, in the denominator we have got radius of the Earth, that is 6.37 into 10 to the power 6 meters. You complete the calculation and show that this is coming out to be 1.12 into 10 to the power 4 meter per second, which in layman's language we might report it to be 11.2 kilometer per second. So you see that if a particle of any mass has to be thrown so that it doesn't return to the Earth's gravitational field, it escapes in the outer space, the minimum speed to be given to the particle will be 1.12 into 10 to the power 4 meter per second, that is 11.2 kilometer per second, a huge speed indeed. And the value we have got here only for the Earth, and the particle must be thrown from the Earth's surface. We shall see later that for different celestial bodies, of course, the value of escape speed keeps on changing. It also depends on the position of throw, that is whether the surface, the mountain top, and so on. Looking into the expression once again, you see that escape speed depends only on the mass and radius of the celestial body whose escape speed is found out. I mean, we are finding out escape speed from the surface of that given celestial body. The particle's mass, the particle that is thrown, that doesn't enter into the calculation. I give you a small work here. Since you know the value of small g at Earth's surface is 9.80 meter per second square, you make use of the second equation, root over of 2g into Re, and corroborate this answer. And never forget this value, which is the escape speed from the Earth's surface. Before I leave the page, I want to give you one more task. I remember giving you a table earlier containing all the data about mass and radius of the 8 planets of solar system. So refer back to the table, collect the data, and calculate the escape speed from the surface of different planets. Once you do that, I don't believe you'll be ever forgetting this formula again. Before I end my discussion on escape speed, I want to discuss a few general finer points about the definition and its calculation. We have seen that for this planet of mass mp and radius rp, when a particle is thrown from its surface, the escape speed was found to be square root of twice g into mass of the planet divided by radius of the planet. Alternatively, you could also write down square root of twice free fall acceleration gp at the planet's surface into the radius of the planet. These equations show that the value of escape speed from a planet's surface depends only on the mass and radius of the planet, and it does not depend on the mass of the particle that is being launched. So interestingly, once we know the escape speed that is valid for any particle being launched of any given mass, be it a huge spacecraft or be it a very light coin or particle or maybe a pebble in your hand, whatever be the case, the value of escape speed will be remaining the same for a given planet at a given point of projection. That is important. The mass of the particle being thrown does not enter into the value or calculation of escape speed. That was my first point. Second point, I would like to say that whenever you define escape speed, it's important to mention from which point on, above or below the surface of the planet the particle is being launched. For example, here we said escape speed from the surface of the planet. The value of escape speed from the surface of the Earth is 11.2 kilometers per second. It's not the same value if I throw the particle from a mountain top or from the bottom of a crater. Let me see these parts in little detail with little bit of calculation. We consider here, suppose a planet of mass mp and radius rp. So same data here. mp is the mass and rp is the radius of this planet. And unlike the usual case, the particle of mass m is not thrown from the surface. We'll consider a mountain on the planet's surface of height h, so that the point of projection of the particle being the mountain top from here, the point of projection is at a distance of not rp, but the distance becomes rp plus h. I have assumed that the height of the mountain is h. So as you launch the particle from this mountain top, what will be the minimum value of this u so that it escapes beyond the planet's gravitational field? And I said already, the answer is not the same as you have done in my earlier calculation. How is it like this? To understand that, let us return to the mechanical energy conservation principle I have said before. We told at the point of launch, if mechanical energy is k1 plus u1, and at the point beyond the planet's gravitational field, the final point of the journey, the mechanical energy of the system, that is particle plus planet system, is k2 plus u2, Let us put the values here with reference to this figure. K1 of course is half m into u square. I have taken the particle's mass to be small m as usual. Now come to this gravitational potential energy for this particle planet system. Earlier it was thrown from here, potential energy was minus gmp into m by rp. But this time the distance between the particle and the center of the planet is not rp plus h. Therefore, my gravitational energy term will be minus g into mass of planet into mass of particle divided by rp plus h, h being the height of the mountain from where the particle is launched. Coming to the right hand side, finally the particle comes to a stop, so k2 is 0 since its speed is 0, and when the particle goes to infinite distance, at a distance where it can escape the gravitational field of the planet, of course u2 is coming out to be minus g into mp into m divided by infinity, and this term also vanishes, is not it? So I could get from here that half mu square is coming out to be, by rearrangement, g into mp into m divided by rp plus h. As you understand, on the right hand side both the terms become 0. This term is also 0, and from this expression once again the mass of the particle cancel out, and you get that the corresponding, well, let me call this u as escape speed now, because I have considered the particle has escaped to infinity. Therefore, the corresponding escape speed is coming out to be how much? Root over twice g into mp divided by rp plus h. The whole thing under square root, and compared this with the earlier result. It was rp in denominator, but this is rp plus h, h being the height of mountain. So you see that if the particle was launched from a higher point than the surface, accordingly escape speed also changes, and the reason is the value of u1. So that is one thing I wanted to show. One more thing comes out from the writing here, that you have seen that if the particle indeed escapes to infinity, in such case the right hand side is coming out to be 0, because this term is also 0. It means that for a particle being launched with escape speed, its total mechanical energy during that travel is 0. That's important. Kinetic energy is positive, potential energy is negative. So whichever be the point you consider during the motion of the particle's journey, at any point the total mechanical energy of the particle escaping beyond the planet's gravitational field is 0. By mechanical energy conservation principle, understand that carefully. I am tempted to show you one more case. Why not take the particle somewhere inside the earth? Let me draw the figure for that. So here is an enterprising man who digs a hole up to the center of the planet. So I am just showing it once again in the figure. As I said, mass of the planet is mp and its radius is taken to be rp. And this is the center of the planet, and this time a hole is dug up to the center of the planet, and a particle of mass m is taken there, and from there it is launched with the given escape speed. The question is, what is the value of this escape speed? Is it same or different? And the answer is different for the same reason as we explained a short time back for the case of a mountain top. Let us see once again here, going to apply this formula only, k1 plus u1 is equal to k2 plus u2, and here I could write down the value of k1 is half into m into u square. What is the value of u1? This time the particle is taken at the center of the planet, and this time a result that we mentioned earlier in my lecture, you should go through and find out. We discussed the gravitational field and potential due to extended bodies. we discussed the case of any spherically symmetric solid sphere, and he had shown there that the gravitational potential at the center of a solid sphere is given by this unusual formula, minus 3 into g into mass of the sphere divided by twice radius of the sphere, minus 3 gm by 2r. Can you remember the formula? We will need it now. U1, the initial potential energy of the particle plus planet system, is coming out to be then minus 3 into g into mass of the planet, a spherical body, into mass of the particle small m divided by twice the radius of the planet. This is a very interesting result, but that is the value of U1 if the particle hypothetically is taken to the center of the planet before the launch. Well, when the particle escapes to infinity, obviously, I have already shown a short time back, K2 is 0 and U2 is also 0. Because at infinite distance, this term comes out to be 0. So, I get from here, by applying energy conservation principle, that half mu square minus 3 into g into mp into m divided by twice rp is coming out to be 0 plus 0. The total mechanical energy of the particle planet system will be 0 at any point during the particle's journey, provided it escapes to infinity, an important result that you might need in future calculations. Coming back to our calculation, I am getting here that half mu square is coming out to be 3 upon 2 capital G mass of the planet into mass of particle divided by radius of the planet. The small m's cancel out, and you get from here the escape speed required to be given to the particle for escaping. Well, the 2's are cancelling. Will you just check yourself and tell me? I can see the 2's are cancelling out, and the value of escape speed is coming out to be square root of thrice g into mass of planet divided by rp. A result that is quite different from the ones we have got so far. Just compare this one with the standard value of escape speed root over of 2 gmp by rp. This is 3 coming, quite different, and this is because I have changed the point of launch. So the whole discussion makes it very clear that it's not only important the celestial body from which the particle is being launched, the escape speed also depends on the point of projection above, on or below the surface of the planet. Very important and interesting. Another point I want to mention here is this: the escape speed from a planet does not depend on the angle of projection of the particle from the planet's surface. So let me show it here. This is a spherical planet, this is the center, and suppose the particle is launched from this position as I am showing here. So I draw the radial direction and the tangential direction. Now whichever be the way of throw, the direction of throw, I might throw the particle radially outwards, I might throw the particle along the tangent drawn at the surface, or at any angle between these two extreme possibilities, along radially or along tangentially, or any arbitrary direction. The escape speed for the planet surface will be remaining the same, independent of direction of projection of the particle. That's an important thing. So another point I want to mention here is that when I gave you the formula for escape speed from a planet, it is escape speed for any particle from the planet's gravitational pull and not from the pull of the solar system. That you must understand. To illustrate the point, when I told you that escape speed from the surface of Earth is about 1.12 into 10 to the power 4 meter per second, or that is 11.2 kilometer per second, which you mean is that this is the speed to be given to a spacecraft if you want to launch it from the Earth to some other planet within the solar system. In case the spacecraft has to escape the combined gravitational pull of the Earth as well as the Sun, in such case, the speed required is more than this, which can be shown to be 16.6 kilometers per second approximately with respect to the Earth's surface. It requires a rigorous proof for that, and I'll try to prove it sometime in my future lectures. So here are a few points about escape speed. I think you are ready now for doing a few problems on this very interesting topic.